Good day, everybody. I would like to give a lecture on introduction to mathematical analysis, an area or a topic which is very essential in mathematics in general and plays a great role in advanced research in mathematics. This area is fundamental, but unfortunately, very difficult for some people to comprehend. And for that reason, I've decided to see if I can give a kind of motivational touch to this by trying my best to reduce the entire thing to basic minimum in terms of understanding. And for us to really capture the message, I would like the listeners to review the following. Review the set of the sets that are related with the set of real numbers, where we know the set of real numbers is represented by R. R denotes the set of real numbers. R denotes the set of real numbers, which is pictorially represented by a line of this form. Somewhere here, it's sort of going to plus infinity. The line represents the set of real numbers and is graduated in such a way that each point on the line represents a number, represents a number which I call a real number. It's graduated in this form, and so on, -1, -2, and so on, and so on. This side, the arrow is a two-way arrow that is going both ways. This one is moving to what which I call plus infinity, and to the left is moving down to minus infinity. And remember that minus infinity and plus infinity are for now notations, depicting where the line will end, if ever it will end. So the set of natural numbers is nothing but what we refer to as the x-axis at elementary level of mathematics. And here, I would like us to recall the following important subsets of R, one of which is the set of natural numbers denoted by n. And this n is nothing but the set 1, 2, 3, 4, and so on. This is the set of natural numbers. If you look at this line, it will be as if to say this side, the right side of 0 is the set of natural numbers. But one should note that in between 0 and 1, there are still infinitely many numbers because each point represents a number, and there are infinitely many points between 0 and 1. So between 0 and 1, we have numbers like, say, 0.001, 0.002, and so on and so forth. So the set of natural numbers starts from the count. We also call them a set of natural numbers. The elements of set of natural numbers are also called the counting numbers. Normally, this is the notation used by Anglophone mathematicians. And we must note immediately that the Francophone mathematicians usually they note the set of natural numbers by same n, but in their own case, it starts from 0, 1, 2, and so on. We should take note of this, and this will come in view depending on the on the material or book the reader or the listener is using. So in the francophone sense, whenever they want to talk about this one, which is usually used by the anglophone mathematicians, they will write n plus. So for a francophone mathematician, n plus stands for 1, 2, 3, and so on. So these are just notational issues. But in this course, I will restrict our attention to n, where n is seen as 1, 2, 3, 4, and so on. Another important set we shall also recall is the set of integers. The set of integers is denoted by z, and it's defined as, please, whenever I put this dot dot before equality sign, it signifies I'm making a definition. So this is nothing but the set that runs from minus infinity. Say we may have minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. And if you look at this set, you'll find out that it naturally contains all elements of the set of natural numbers, meaning that the set of natural numbers is a proper subset of Z. Then the next set, which is important to us, is what we call the rationals, the set of rational numbers, and is denoted by Q and defined as the collection of all P over Q, so that P and Q are integers. P and Q are integers, but with the restriction that Q is not equal to 0. Now, this set is the collection of all those numbers we can write as exact fractions, as simple ratios. If you look at the set of natural numbers and the set of integers, you'll find out that every natural number, if I use n, for instance, to denote a natural number, then this n can be expressed as n equals n over 1. So in that particular case, it means that n can be expressed as a rational number. So n over 1 is in the form this, where n in this case, where p is equal to n and q is equal to 1. So whenever I take n in the set of natural numbers, I can express n in this form. This therefore means that this therefore means that the set of natural numbers is a subset of the set of what? Of rationals. Similarly, Z, the set of integers, is also a subset of rationals. But importantly, we must note that the inclusion here should be a strict inclusion, in the sense that the set of natural numbers is properly contained in the set of rationals, and the set of integers is properly contained in the set of rationals also. Now, let us note the following. Observe that n, the set of natural numbers, is a proper subset. This is the proper notation to use, because its proper subset means that every element of natural numbers is in the set of integers, but there is a particular integer that is not in n. And the set of integers is also a proper subset of the set of rational numbers. In turn, the set of rational numbers is a proper subset of the set of real numbers. So these inclusions hold. Further to this, there is another set, which is the set of irrational numbers, we denoted by Q complement. This set contains all elements that are not expressible as simple as exact fractions. or ratios. Members of Q complement include all sorts, all sorts, all sorts, e.g. root 2, all sorts, e.g. root 2, root 3, root 7, root 7 are all irrational numbers. Root 2, root 3, root 7, and so on are all irrational numbers. Numbers like pi, where pi is the ratio of the circumference of the circle to its diameter, is also an irrational number. The number e, where e is the base of natural logarithm, the exponential e, is also an irrational number. So irrational numbers are those numbers we cannot express as exact fractions or ratios, or numbers we cannot express numbers that do not have recurring decimal points. Let us note that a number like 0.6666 and so on is a rational number, because 0.6666 is something like 2 over, can be expressed as 2 over 3, which is in the form P over Q, where in this case P is equal to 2 and Q is equal to 3. So number like 0, let me put it here, 0.6666 and so on is an element of what? Of Q, because we can express this as is as recurring decimal, and we can write it as what? 2 over 3. So 2 over 3 is in the form P over Q. So we now see what the irrational numbers are. Numbers that we cannot express as rational numbers. And we now have the following, that if we take the union of Q and its complement, that is irrational, the union of these two sets will give us the entire R, which is the set of real numbers, while the intersection, why they do not have anything in common, meaning that their intersection is an empty set. This notation is for empty set. So these are some of the sets that we have as special subsets of R that will play great role in what follows. Another important subset of R that will play roles in what we shall discuss are the intervals of the real line. Where, for instance, if we take I as a subset of R, if we take I to be a subset of R, then I is called an interval. If and only if for any x, y, we pick in I, any other point z in R, such that s dot such that x is less or equal to z, less or equal to y. If we do this, we have that z belongs to I. What this means is that to get an interval, to see what an interval is, it means that whenever we are given 2 points in that set which I call an interval, any other point lying between the 2 points given must also be in the interval. So we have some examples of intervals of R. Let us look at the following examples. Examples of intervals of R. Assuming that we are given A, B in R such that A is less than B, then the set denoted by AB or AB defined by AB equals AB equals the collection of all x in R so that A is less than x less than B is an interval of R, and this interval is an interval of R called the open bounded interval. The open or called an open bounded interval. Let me use, for some reasons, the indefinite article, an open bounded interval, for some reasons. An open bounded interval. So this is what we shall call an open bounded interval. And it's such that whenever you pick any 2 points there, any 2 points you pick there, say x and y, must be such that they lie between A and B. A and B are not included. And they are such that whenever you pick any other point in between them, that point you pick in between them must also be in that set AB. And I must point out here that these notations are very essential. We have to be very careful when making use of these notations. For instance, the curved bracket, using the curved bracket to denote this set is the conventional thing that normally happens at the elementary level. This is how the interval is defined. Then this particular one is used, it's more technical in the sense that if I have this as the real line, and if here is A and here is B, then the set in question, which is the open bounded interval, is the collection of all points x lying between A and B, with A and B not inclusive. So in that case, it's natural to do this kind of thing, and I'll put here. By this notation, it means that B belongs to this side, to the right-hand side, while A belongs to the left-hand side. So it's not A and B are not within this range. So that's it. But why this notation is brought in now is to avoid confusion when there is a mathematical discourse involving the set of real numbers and say the Cartesian plane, that is the two-dimensional Euclidean space R2, in which we normally denote a point there in this form. a point in R2 is in this form. So to avoid confusion when these two sets are playing roles in a particular mathematical discourse, to avoid confusion, it's preferable to use this notation for an open interval while we retain this particular thing for a vector in R2. So there are about 9 prominent intervals of real line. One of them is the one I've just mentioned, the open bounded interval. The other one is, which is also very important. Maybe I'll label this one I. Let me label it, or there's no need labeling it. I think we'll follow. So another one is if we are, okay, let me say here, why I call here, why I put here I here. I think it will make sense that way. Let me put it right, correct. So here we have I. Why this one is I. Here we're given A, B in R such that A is less or equal to B. And then the set denoted by AB and defined as AB equals the collection of all x in R so that A is less or equal to x less or equal to B is called a closed bounded interval. A closed bounded interval of R. Let us note that these two words are very important. The same with these ones within where we have open bounded intervals. I underline these words for a very important purpose, which we shall see in the near future. Then there are other intervals. So, for instance, we have something like I'll just list them. Maybe I'll define one more, then try to list others. Another one is the one we may write as, say, AB in R given. Then we look at something like AB, which can be written as A, comma B, and this is equal to the collection of all x in R, so that A is truly less than x, but x is less than or equal to B. We note here that A is not part of the set. Here, in this case, both A and B are members of this set. Here, A is not a member, while B is a member. And if we can depict this one pictorially, this is a situation like this, where we have, say, A here and B somewhere here. B is a member, while A is not a member. So if I put this symbol here, it means that A belongs to this side. If I put this, B belongs to the left side too. So we are talking about all the points that are here, including B, but does not include all x that lie between A and B with B inclusive. The same thing with here. Here we have here for the closed bounded interval, we have a collection of all points that are between A and B, with both of them inclusive. So we have the points, a set of points here. Remember that as A and B vary in R, these intervals also vary. For instance, if A equals, say, 2 and B equals, say, 5, we have maybe the closed bounded interval 2, 5, as the case may be. The number I, V is the set given AB in R. We have the set, say, A, B is closed at B. That is, A is closed at A is inclusive, but B is not inclusive. That is closed at A or open at B. And this can be written as A, comma, B. And this is nothing but the set of all points X in R, so that A is less than or equal to X, but X is less than B. This pictorially is nothing but a collection of all points between A and B, but in this case, A is inclusive, but B is not. So we have the collection of all the points that lie between A and B, with A being a member and B is not a member. We still have other ones, like V. Here, if we fix A in R, we can talk about a set of the form that is denoted by, say, minus infinity A. This one, which we can still write as minus infinity A. This is nothing but the set of all points X in R, so that minus infinity is less than X and X is really less than A. And this is still equal to the set of all points. We can simply write it as the set of all points in R, so that X is less than A. We also have what we may call minus infinity A, but this case closed at A. This is the same thing as minus infinity A. And this is nothing but the set of all points X in R, so that minus infinity less than X, or X is less or equal to A. And this is nothing but the set of all X in R, so that X is less or equal to A. I may even write this as number 6. So we take A in R and we define this. All these are intervals in R. And for this last one I've just put, if pictorially we may have something like this. Somewhere here, this direction is going to minus infinity. Somewhere on the line we have A. So for this particular one, what we are talking about is the set of all points that lie below A, with A inclusive. That's what this set represents. This particular one will represent the set of all points that lie below A, but in that case, A is not inclusive. Now, we go further to introduce others. Let's look at this one, V, or VII. Sorry, let me see. Okay, okay, good. VII, VII, VII. Here we take A in R. Remember that A is an arbitrary element of R, and we now look at the set, say A plus infinity. This is the same thing as A plus infinity. Remember the explanation I gave about these notations. And this can be defined as the collection of all x in R so that a is less than x and x is less than plus infinity. And this is nothing but the set of all points x in R so that x is greater than a. And please let us note that as I mentioned earlier, infinity, both minus infinity and plus infinity are not real numbers. They are just symbols representing where we assume that the line will end both ways. The one, that is, if you look at the arrow, you find out that the arrow is pointing where the line is going to. And if it will ever end, wherever it ends is what we refer to as minus infinity. The same thing with the other side. If it will ever end, wherever it ends is what we refer to as plus infinity. But these two numbers are not real numbers. It may be in future when we get to for more advanced part of this course, we may come to a situation whereby these two numbers will be recognized and be thrown thrown into a set that will form a new set, which I look at as R bar, which is R, the set of real numbers, union minus infinity plus infinity. In that case, we'll be talking about what we call extended real numbers, but for now, is above the scope of what we are discussing. Now, the next one is what I call VIII. And in VIII, we take A in R, and we look at the set A plus infinity, and this is equal to the set of all. This is also can be denoted by A plus infinity using this symbol, and this is equal to all x in R, so that A is less or equal to x and x is less than plus infinity. And this is the same thing as all x in R, so that x is greater or equal to A. This set is also an interval. Remember that what I'm listing are all the possible intervals on R, on the set of real numbers. Considering what is always presented to students at this elementary level, the last one that is usually presented is the one I'll call IX. IX is nothing but the interval minus infinity plus infinity. And this can be denoted by minus infinity plus infinity. And this is nothing but the collection of all x in R, so that minus infinity is less than x and x is less than plus infinity. This set is nothing but R itself, the set of real numbers. So you see that the set of real numbers is also an interval. And it is trivial in the sense that if you take any two real numbers, any point z between the two real numbers you picked is also what? A real number. So it satisfies the definition we give above as a definition of interval. Now, we now look at some special cases. Special cases of sets. Here we look at some special sets that are still intervals. For example, if we fix x naught in R and consider the set that contains only x naught. The set x naught, that is the singleton x naught. There's one obvious thing that looks funny but is true. If we take any xy in this set, it's easy to say that any other point between them will also be in the set. That is, if we take any x, y in this set, it's obvious that any point z between the 2 points we pick will be in the set. But the way I'm looking at it, people will be confused. To make it clearer, pick x, y here. What it means is that x, if we say given x, y in that set x naught, then x must be equal to x naught, and y must also be equal to what? X naught. Thus, if z is such, if z in R is such that x is less or equal to z, less or equal to y, this implies this is equivalent to x naught is less or equal to z, less or equal to x naught, which is equivalent to z is equal to x naught. So what does this mean? This means that if I take any 2 points x, y in the singleton x naught, then any z that belongs to that lies between x and y will turn out to also be what? X naught. And this implies that what? This implies that z is what? Is in the singleton x naught. What does this mean? This means, therefore, that this singleton x naught is an interval. X naught is an interval. X naught is an interval. And it is easy to see that this interval x naught can be written in the form x naught, x naught. And this is nothing but the collection of all x in R, so that x naught is less or equal to x, less or equal to x naught. So every singleton subset of R is an interval. Every singleton subset of R is an interval. Another special case is the case II. And this case here, we consider the empty set. The empty set of this, the empty set. It's obvious that the empty set is an interval. But how would one say this? Empty set is a set that contains nothing. Empty set contains nothing. There's nothing in the empty set. In other words, what this means is that the cardinality of the empty set is equal to 0. There's nothing in the empty set. So how then can we justify that the empty set is an interval? Remember what the definition of an interval says. The definition says that if we are given any 2 points in the set, then another point lying between the 2 points must also be in the set. Now, for us to justify that the empty set is an interval, we need to take 2 points in the empty set and show that the point between them is in the empty set. Now, this is a kind of what I may refer to as back to sender in the nomenclature of certain group of people in where I'm coming from. What I mean is when you are asked to show that the empty set is an interval, you may request the person to give you 2 points in the empty set. And once the person produces 2 points in the empty set, then I will show the person that any other point between the 2 points is also in the empty set. And when the person is not able to give me 2 points in the empty set, I will now request the person to agree with me that the empty set is what? Is an interval. And interestingly, this empty set as an interval can be written this way. I may decide to write the empty set as in the form of an interval as follows. Maybe I would write the empty set as equal to, say, AA, where A is a real number, or A, and this could be written as the collection of all x in R so that A is less than x less than A. Of course, if you look at this definition, you'll find out that it depicts is nothing but an empty set, because this is a contradictory statement. That A is less than x less than A means that A is truly less than itself, which is a contradiction, meaning that this set contains nothing. So this is a kind of an intuitive way of expressing an empty set as an interval. That's it on the intervals. But there are other things I would like to point out on the that is concerning these intervals. If we now recall the ones I talked about above, for instance, the open interval AB, open bounded interval AB, and the closed bounded interval AB. These intervals, look at these ones, these intervals. I want to make some remarks on them. This one, the remarks I want to make is that if you are reading some maybe some materials that discuss these sets, they will look at this as a closed finite interval. This one open finite interval, and this one they will look at it as closed open finite interval. This one open closed finite interval. My worry there, and what I want to really put in the right perspective, is the use of the word finite. That finite does not necessarily mean that these sets are finite. We have to be very careful. These sets are not finite sets. In fact, by the way, what is a finite set? For easy understanding, a finite set is a set whose cardinality is either 0 or a natural number. Is a set whose cardinality is either 0 or a natural number. For example, the empty set is a finite set because its cardinality is 0. The singleton I mentioned above is a finite set because its cardinality is 1, which is a natural number. Any set whose cardinality is a natural number is a finite set. These particular sets we have here are not finite, because if you take the number, if you, for instance, in this case, you take the set, say 2, 3, this set is not finite because its cardinality is not a natural number. Looking at this set, you will find out that between 2 and 3, there are infinitely many points. There are uncountable number of points. There are infinitely many points that lie between 2 and 3, 2 and 3 inclusive. And for that reason, the cardinality of the set of points lying between 2 and 3, 2 and 3 inclusive, is not a natural number. And therefore, this set is not what? A finite set. So when you now hear authors talking about finite closed interval, finite open interval, and so on and so forth, we should understand it from the perspective that they are looking at the distance, the length from here to here. So they are looking at the interval of finite length. Finite length means measuring the distance, using tape to measure this from here to here. Whatever that gives us is what they use to measure, what they use as to describe this. So it does not necessarily mean that this set is finite, rather that the set is of finite length. But unfortunately, we've not discussed what length is. And for us, it's until that is discussed, or what distance is. It's something what is discussed that will not make use of it and bring out what it means to say that this has a finite length or that is of finite length. So it's on the when putting into consideration the length of the interval that they now use the word finite. Okay. So that's what I want to point out. Now, there is an important notion actually this lecture. Remember that what I did above, I just review. This particular lecture is targeted on looking at what we call the absolute value function. Absolute value function. Absolute value function. This absolute value function is denoted by the symbol. Look at these two bars with dot in between. That's the symbol we use to denote absolute value function. And the absolute value function is actually a map from R to itself, to R. In particular, the absolute value function actually maps R to the interval 0 plus infinity. This is the actual range of the absolute value function. And the absolute value function is defined on every real number as follows. Given x in R, this number, absolute value of x, this is what we call absolute value of x. Absolute value of x is nothing but the value the absolute value function produces when it acts on x, on a real number x. The absolute value of x is defined as follows. Is defined as x if x is bigger than 0, and 0 if x is equal to 0, and would be minus x if x is less than 0. And I want us to note that in this definition, if is seen as if and only if, because it should be a two-way thing. So whenever we are given a definition, we assume that any if that appears in the definition is if and only if. Okay. So, and this can still be written in a shorter form as x if x is greater or equal to 0, meaning that I'm combining these two. And it will be minus x if x is less than 0. So this is the absolute value of x. And for example, assuming that we want to compute, say, absolute value of 2. Given the number 2 in R, absolute value of 2 is nothing but 2. The reason is because since 2 is bigger than 0. Absolute value of 0 is, of course, 0 by definition. Say absolute value of minus 5 is by definition minus 5. And this is because since minus 5 is less than 0. So definition says that if x is less than 0, then absolute value of x will be minus x. So that's why we have here this. And minus 5 is nothing but 5. So absolute value of minus 5 is 5. Now, pictorially, we can even look at the graph of the absolute value function. The graph of absolute value function is nothing but an identity function on the non-negative side of R. It becomes the identity, and this side will give us the mirror image of that identity function. Please, if this is properly drawn, it's expected that this part should be the mirror image of this part. Please don't mind my hands are shaking, but the and that makes the diagram. This is supposed to be a straight line that should be the mirror image of the identity map on this side. So this is the graphical representation of absolute value of a number. Assuming that here is x, it is expected that if you trace the value of x up the curve and you come this way, what you get here is also x. Reason is because x is greater than 0. Observe that at 0, the absolute value of 0 is still 0. So the absolute value of 0 is 0. Now, remember what I explained, that is expected that this curve should be the mirror image of this one, seeing the vertical axis as the mirror. Now here, if we take, assuming that here is minus 1, our expectation is that if you trace the value of this curve, what you get here will be 1. So the absolute value of minus 1 is 1. Good. So this is the sort of graphical representation of absolute value of x. Absolute value of x. And there's one other thing I want us to observe. If this is perfectly drawn, maybe using the right instruments to draw, it's expected that this curve can be drawn without removing pen from paper. And intuitively, what it means is that this is a continuous curve, meaning that the absolute value function is a continuous function. I use the word continuous in quote because we've not talked about what continuity means. I'm saying this for us to bear it in mind so that when the time comes and continuity is mentioned, when we pull up the absolute value function as an example of a function that is continuous, we'll understand where it's coming from. And then another interesting thing is that, as I said, if this curve, the right instruments are used to draw this curve and we get the right curve, then this particular place where it touches the origin, where it touches 0, that place will be where two lines meet. Think about it as where two ends of needle. That is, if you take needles, two needles, that sharp end meeting at that point, that's what it will look like. And why I'm saying this is that if you look at that sharp end where the needle meet, if somebody rubs the palm on that particular place, it will definitely, depending on how hard the person does that, it may tear the person's palm. This means that this place is not smooth. And what this signifies is that this absolute value function is not differentiable at the origin. So let me just leave it at that for now until we get to discussion on continuity and differentiability. Now, look at here. Let us look at some properties of absolute value function. Absolute value function. Some of the properties are as follows. Now, let me put this as proposition 1. For any x we pick in R, the following hold. The following hold. 1 is that x is less or equal to absolute value of x. 2 is that minus absolute value of x is less or equal to minus x. Of course, this one trivially follows from this one by multiplying both sides of the inequality by minus 1. And in that case, the inequality reverses. So the major job should be to get that I holds. 3 is that minus x is less or equal to absolute value of x, and which will also lead us to 4. 4 is saying that minus absolute value of x is less or equal to x, meaning that if we are able to get establish 3, then 4 holds. Now, I will only, for want of time, I will only justify proof of So how do we do this? Two cases arise. Two cases arise. And what are these two cases? Case one is the case where we assume that x is greater than 0. If x is greater than or equal to 0, then absolute value of x is equal to x. That is, x is equal to its absolute value. So here is the case where equality holds. Remember, we are trying to show that this inequality holds. Then case 2 is the case where we assume that x is less than 0. Here, if this is the case, then absolute value of x is equal to minus x. Is minus x. And we note that x less than 0 implies minus x is greater than 0, or 0 is less than minus x. Therefore, in this case, x is less than 0, which is less than minus x, and this minus x is its absolute value. So this means that here x is less than absolute value of x. So when x is less than 0, x will be less than absolute value of x, and when x is greater or equal to 0, x will be equal to absolute value of x. Thus, putting these two together, so from the two cases, we conclude that x is less or equal to absolute value of x. That is for any x, so x we pick in the set of real numbers. So others, the number I, and IV follow the same pattern. But the major job to do here is to justify the number I holds. The other two will trivially follow. That's it. Then another property of the absolute value function, I'll put this as proposition, but I will not justify proposition 2. Here, what he's saying is given m greater or equal to 0 and x in R, if we do this, then the following are equivalent. Given m greater or equal to 0 and x in R, then the following are equivalent. I is that absolute value of x is less or equal to m. And II is that minus m is less or equal to x less or equal to m. So we are saying that these two are equivalent. So that's another important property of the absolute value function. And I will leave this for the listeners to justify. And the way to go is to assume that this is true and prove that this holds. Then next, one should assume that this is true and prove that I holds. Equivalence means that this if and only if this. This if and only if this. So you assume that I holds and prove that, show that 2 also holds. And next you assume that I holds and show that I holds. I think is a good exercise to do. Then proposition 3. Proposition 3. Here, given x, y in R, then the following hold. I is that absolute value of x is greater or equal to 0. This follows from the definition of the absolute value. And absolute value of x is equal to 0 if and only if x equals 0. This also follows from the definition. Another interesting one is that if I have the product of two numbers x and y, and I take their absolute value, then the absolute value of the product will be the same thing as the product of the absolute values. This also is interesting to look at, and I would like the readers to the followers or the listeners to look at this, try to justify this, exploring different cases. Then this is number I. This is number IV. The number IV is telling us that if I take sum of two numbers x and y and take the absolute value of the sum, then the absolute value is less or equal to the sum of the individual absolute values. In fact, my emphasis is the essence of giving this property is to lay emphasis on number 4. All the other ones are very important, but they can easily be justified. But where we normally have problem is in the justification of number 4. This number 4 is called the triangle inequality. The triangle inequality. The problem with this number is that at times when some people are trying to justify it, they will bring in something like squaring something and expanding, applying inequality, and then eventually it will come to a point of taking square root. That square root of 18, there are a lot of things behind it. A lot of conditional statements should be made before that kind of proof will work. For that reason, I decided to look at that number 4, trying to provide a means of explaining that is true without going through this idea of taking square root or squaring anything. So to justify number IV, the whole thing borders on the initial properties we gave. This particular property here is the key. So we should recall that the justification of the recall of that minus absolute value of x is less or equal to x, and x is less or equal to absolute value of x from that proposition 1. And that minus absolute value of y is less or equal to y, and y is less or equal to absolute value of y. Say, almost repeating the same thing, but with the values x and y. Now, if I add these two inequalities, I have therefore that minus absolute value of x plus minus absolute value of y will be less or equal to x plus y, and x plus y will be less or equal to absolute value of x plus absolute value of y. Now, putting these two together will give me, therefore, that minus into absolute value of x plus absolute value of y will be less or equal to x plus y, and this x plus y is less or equal to absolute value of x plus absolute value of y. Now, what does this bring me to? This brings us to the property we mentioned above, where we say that these two are equivalent. And remember, I left the proof as an exercise. These two are equivalent. Now, if you look at this, you'll find out that we've landed at something that resembles number ii. And since we've landed at something that resembles ii, that resemblance must give us that number ii. Number I is true since they are equivalent. So here I have that this holds. Now here, if we remember that by the property of absolute value as mentioned above, that this is greater or equal to 0. This is greater or equal to 0. So seeing this as our m and this as m, so here will be minus m. If we look at this as x in proposition 2, it will mean therefore that this inequality is equivalent to absolute value of x plus y is less or equal to absolute value of x plus absolute value of y. We have this, and that's the inequality we are looking at. And you'll find out that this reduces in these few lines without bringing in anything square or taking square root. No, so that inequality holds. Then the next property, which is very important, I'll put it as proposition. I think this is proposition 4. What does this proposition say? What it's saying is that for any x, y you give me in the set of real numbers, I'll have that absolute value, let me put I, absolute value of x minus absolute value of y will be less or equal to absolute value of x minus y. And I, absolute value of x minus absolute value of y is less or equal to absolute value of x plus y. I must warn here that this particular number 2, I just put it there for computational purposes, is true. And but the most frequent one in use is that almost occurs whenever you want to do certain computations is this one. This first one is very, very important and should be noted. It will play a role in so many things. This will play a role in showing that, for instance, when we get to sequences, it will help us to show that every convergent sequence is bounded, that every Cauchy sequence is bounded. It will also help us to show that the absolute value function is continuous, and not just continuous, but uniformly continuous. We shall see that when we get to the discussion on this concept. So this inequality must not be played with. It must be remembered. So now, and for that reason, I would like to lay further emphasis on it by trying to justify it. So, um, uh, justification of, we want to justify the fact that for any x, y in R, absolute value of x minus absolute value of y is less or equal to absolute value of x minus y. This is what I want us to justify. This is what I want us to justify. So let's see whether we'll be able to do justice to that. So to do that, justification, I want us to observe that for any x we pick in R, absolute value of x is equal to absolute value of x minus y, or rather for any x, y we pick in R. For any x in R, for any y in R, absolute value of x minus x is equal to absolute value of x minus y plus y. So that if I look at this as an entity and this as the second entity with plus separating them, I can apply triangle inequality to get that this is less or equal to absolute value of x minus y plus absolute value of y. This means, therefore, that absolute value of x is less or equal to absolute value of x minus y plus absolute value of y. Plus absolute value of y. So this is less or equal to absolute value of x minus y plus absolute value of y. And from which we get, therefore, that absolute value of x minus absolute value of y is less or equal to absolute value of x minus y. I may label this 1. If we label this 1, then we go further to look at here. Some people, some students normally get confused here. Whenever they get to this level and they get this kind of thing, they will assume that they've gotten what is required. Remember that what you have here is absolute value of these two, this difference. So this absolute value doesn't fall from heaven anyhow. Doesn't fall anyhow. One has to be very careful, because what some people usually do is that once they get this, they think they've gotten it, and they will just insert absolute value here, and maybe think they've gotten the thing. No. The reason is because here could be, say, -4 when you evaluate it. Y here is, say, 2. -4 is obviously less than or equal to 2. But if you apply absolute value on both sides, you get something that will be somehow contradictory, because you get, instead of getting that 4 is less than 2, you get that 4 is bigger than what? Is bigger than 2. So taking absolute value on both sides of inequality is not true always. So for that reason, we have to take the other side of it, where we'll now start with y and look at absolute value of y and express it as absolute value of y minus x plus absolute value of x. And this again will be less or equal to absolute value, absolute value of, let me correct something. Here must be, what I'm looking at is absolute value of y minus x plus x in absolute value. So that we can apply triangle inequality to get absolute value of y minus x, then plus absolute value of x. And this will therefore give us that absolute value of y minus absolute value of x will be less than or equal to absolute value of y minus x. But we must do something here. Let me put aside here. I didn't want it to obscure what we are doing, but it's true. Look at here. We should note the following, that for any x, y we pick in R, absolute value of x minus y is the same thing as absolute value of minus x plus minus y. I believe we will agree with this. And this is the same thing as, let me hope that we are saying it. This is equal to absolute value of minus is now common. I'll bring it out and I have minus x then plus y. And this will give me exactly the same thing as absolute value of minus into y plus minus x. But plus minus is minus, so this will be absolute value of minus y minus x. I'm doing this intentionally, not that I cannot just simply jump that this is equal to this and I'll continue. No, but I'm doing it intentionally so that everybody will be carried along. So this is equal to absolute value of minus 1, then absolute value of y minus x. And what does this mean? Absolute value of minus 1 is 1. So this will end up giving me absolute value of y minus x. So what this means is that absolute value of y minus x is the same thing as absolute value of x minus y. And that will allow me to put equal to here and write x minus y. So what I've gotten therefore is that absolute value of y minus absolute value of x is less than or equal to absolute value of x minus y. Now going further, I can still manipulate here algebraically by rewriting this in the form of this particular inequality is equivalent to minus into absolute value of x minus absolute value of y is less or equal to absolute value of x minus y. These two are exactly the same, because by the time you open up this bracket, you find out that you get this. So having got this, I can now multiply both sides by minus 1 to get therefore that absolute value, sorry please, I'll get therefore that minus absolute value of x minus y is less or equal to absolute value of x minus absolute value of y. And this I'll call 2. Now, combining 1, if we combine 1 and 2, combining 1 and 2 gives, in fact, let me say combining 2 and 1. I think it's better that way so that it will follow that order. Combining 2 and 1 gives from 2 minus absolute value of x minus y is less or equal to absolute value of x minus absolute value of y. And this will be less or equal to, I'll get it from 1. From 1, I'll get that absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. So I just insert absolute value of x minus y here. So I have that this inequality holds. And looking at this again, you'll find out that it brings forth something that resembles what we have in proposition 2, where this is m. This is m. So we have something like minus m is less or equal to x, less or equal to m. And this therefore will be equivalent to absolute value of x, which in this case is absolute value of x minus absolute value of y. That will be less or equal to absolute value of x minus y. And this is the required inequality. This inequality, as I said, is very important. Now, before I conclude, let us note that in the equivalence expressed in proposition 2, that the inequality will still be strict, meaning that what I'm trying to say is that absolute value of x less than m is equivalent to minus m is less than x less than m. This inequality also holds, and it follows from that proposition too. But here we have to be very, very careful by making sure that we retain the inequality, make the inequality straight. So what I'm trying to say is that the inequality in proposition 2 could still be changed to strict inequality, and this result still holds. Now, I think this is a good point to stop this lecture, this particular one. But before that, I would like to exercise. Number I would like the listeners to maybe do these simple things. Find the range of values of x so that absolute value of x plus say 3 is less than 1. Let me call this number A. Number B, absolute value of x minus 5 is less than minus 6. Number C, same, absolute value of x plus absolute value of x minus 3 is less than 2. Number II, express the set of values of x in R such that absolute value of x plus 5 is less than or equal to say 3 in set builder form. In set builder form. In set builder form. So I think with this, we shall call it a day at this juncture. Hoping to see you soon. Thank you for listening. Please note that your comments are highly welcomed. If you have questions, you can put them down on the comment section. Thank you so much.